Okay, now the last thermodynamic process, which is the adiabatic process. Okay, adiabatic process. So what is actually adiabatic process? Okay, adiabatic. Adiabatic process, the key for adiabatic process is no heat flow. Q equal to 0. No heat flow. No heat flow is allowed. Why no heat flow? Because it is using a well-insulated container. Okay, it is using a well-insulated container, so no heat can flow in or flow out. No heat can flow in or flow out, so Q equal to 0. It's a well-insulated container. Yeah, no heat can flow in or flow out. Unlike the isothermal process is using a good conductor container, so the heat can easily flow in or flow out. But for the adiabatic process, it using a well-insulated container, so no heat can flow in or flow out of container. So the Q is always 0. No heat flow at all into the gas, or no heat flow into the gas, no heat flow out of the gas. Okay? So now, Q equal to 0. And then for adiabatic process, how is it different from the previous three processes? If you look at the name itself, we have first we have isobaric. We have three iso actually. We have isobaric, we have isochoric, we have isothermal. Three iso, isn't it? We have isobaric, we have constant pressure, we have constant volume, we have constant temperature. We only have pressure, volume, and temperature. Only three, isn't it? So each of these we have Charles law, pressure law, Boyle's law. Yeah. Constant pressure, constant volume, constant temperature. What else is constant? No more, isn't it? So we only have three iso. So this one is not iso at all. We don't. So that means for this one, the pressure, the volume, the temperature all changes. None is constant. Because we already have constant pressure, constant volume, constant temperature for three iso. This one is no iso. No iso means none is constant. All the pressure, volume, temperature all changes. All changes. Just look at the graph. We have P1, V1, T1, and P2, V2, T2. All this you can use this equation. Okay. All changes. None is constant. Pressure changes, volume changes, temperature changes. Is it true? Okay. You look at this one. Point 1 and point 2. We have point 1 and point 2 here. Point 1 is pressure 1, 200 Pascal. Volume 1, 10 meter cube. And point 1 is at temperature 1, 400 Kelvin. Okay. When it go to point 2, it dropped to a lower temperature, 300 Kelvin, T2. So point 2 has pressure 2, 50 Pascal. It has volume 2, 20 meter cube. It has 300 Kelvin, temperature 2. You see? P1 different from P2. You see? P1 different from P2. V1 different from V2. T1 also different from T2. All changes, or all three changes, pressure, volume, temperature, all changes for adiabatic process. Okay. Before that, we have choric, isobaric, isothermal. They must have at least one constant, either pressure constant, volume constant, or temperature constant. But this adiabatic, none is constant. All pressure, volume, temperature changes. And then I'm doing comparison, yeah. And then regarding the first law of thermodynamics, another important thing is, look at this one. For isochoric process, work done is 0. Work done is 0. For isothermal process, delta U is 0. Adiabatic, Q is 0. First law of thermodynamics is this, yeah. This is our first law of thermodynamics. Let's look at this equation. First law of thermodynamics is Q equal to delta U plus W. So we also have three things. Just now about the pressure, volume, temperature, we have three things. This one, first law of thermodynamics, also we have three things. We have heat flow, we have delta U, we have W. So there are also, I'm doing comparison now. Yeah. For if you look again, isochloric process, work done 0. Yes, taken out work done 0. Isothermal process, okay, isothermal process, delta U is 0. Adiabatic process, Q is 0. So we haven't mentioned what process? We haven't mentioned the isobaric process. We already have W0, we already have delta, we already have W0 isochloric process, we have delta U0 isothermal process, we already have Q equal to 0 adiabatic process. So already take up 3. So isobaric process, none is 0. It has all 3. It has Q, delta U, and W. It has all 3. Unlike the other 3, they only have 2 of it. Yeah, like this one, isochloric, when W is 0, they only have Q and delta U. But for isobaric process, none is 0. Q equal to delta. You have Q, you have delta U, you have W. Okay. So these two. Okay. Now let us look at. So for adiabatic process, the heat flow is 0. Why heat flow is 0? Because it's using well insulated container, so heat cannot flow in and flow out at all. Now let us look at the first law of thermodynamics. Okay, you see, when Q is 0, so what happened? So when Q is 0, so only we're left with delta U and W. Okay, W go to the other side, it becomes negative W. So delta U is equal to negative W. Okay, so when W is negative, so negative, delta U become positive. Okay, and when W is positive, negative positive, you get delta U negative. Okay, so negative positive, negative positive, negative. Okay, now let's look at what it means by this. Let us look at what it means by this. What does it mean by W negative? Let us start from the work done. Okay, let's start from work done. Okay, W negative means work done on gas. That means the gas doesn't do any work. The gas doesn't do any work. Work done on gas, the gas doesn't do any work. Work done is negative. Compression, volume decrease, compression. Work done on gas. So work done on gas, what does it mean? Work done on gas, that means the gas is gaining energy or losing energy? Work done on gas. You learned before this, yeah, in previous videos. When work done on gas, when work done on gas, the gas gain energy. The gas gain energy, isn't it? The gas gain energy. Work done on gas, the gas gain energy. But you look, this container is well insulated. When work done on gas, when W is negative, the gas will gain energy. The gas will gain energy. Okay, work done on gas, the gas gain energy. But the energy that comes in, in the form of work done, the energy comes in where it goes. It's stored inside the gas. The energy that comes in the form of work done, it doesn't go anywhere. The energy that comes in the form of work done, it doesn't go anywhere. It doesn't exit in the form of heat because it is well insulated. It is well insulated, so the heat cannot flow out. Heat energy cannot flow out. No heat loss at all. No heat loss. So all the energy that comes in, into the gas in the form of work done is not going anywhere. is stored inside the gas in the form of internal energy. So what happened to the internal energy? The internal energy will increase. So when work done on gas, the gas will gain energy. So the internal energy will increase. Delta U will be positive. Internal energy increase. Internal energy of the gas will increase. The temperature of the gas will increase. Okay? So when the energy comes in the form of work done, all the energy is stored inside the gas. No heat loss at all. Well insulated. No heat loss. So the energy is stored inside in the form of internal energy. The internal energy increase. That's one of it. Now, how about the second one? When what happened to the second one? Okay, second process is what happened if W positive? What happened if W positive? W positive means the gas do work. Just now, the gas doesn't do any work. The gas doesn't do any work, so work done is negative. Now the gas is doing work. The gas is doing work, so work done is positive. Work done by gas is work done positive. When the gas do work, work done is positive. So when the gas do work, it lose energy. When you do work, you lose energy, isn't it? You won't do work and you gain energy. When you do work, you lose energy. So you see, when the gas do work, the gas lose energy, isn't it? When the gas do work done by the gas, when the gas do work done positive, when the gas do work, the gas lose energy. How it do work? He push up the piston. He push up the piston. He do expansion. The volume increase. He push up the piston. When the gas push up the piston, the gas uses its own internal energy to do the work. He use up his own internal energy to do the work. So he will lose the internal energy. That's why internal energy will decrease. Delta U is negative. The temperature of the gas will decrease. The gas will become colder. Last time it's become hotter. This time, when the gas do work, it lose energy. Why he lose energy? Because the gas use up its own internal energy to do the work. So his own internal energy will decrease. His own temperature will decrease. So when the gas push the piston up, when the gas do work by pushing the piston up, it's actually using its own internal energy to push the piston up. So when he uses his own internal energy to push the piston up to do the work, he lose energy. He lose his own internal energy. Okay? So that's it. So actually, this process from 1 to 2, I want to explain now. Why is it isothermal process and adiabatic process? Both of them are curved line. But why adiabatic process is steeper? The curve for the adiabatic is steeper compared to isothermal. Why? Because for this process, we use this example. We use this the second example to explain. For this process, you see, this is what? From 1 to 2, it is going to the right. From 1 to 2 means it's volume 1 become volume 2. From 10 become 20. So this is expansion, isn't it? This is expansion. The volume increase. Sorry, again, I should write better. From volume 1 to volume. So from volume 1 going to volume 2, actually the volume increase, isn't it? So the volume increase. This is work done by gas. So actually this work done, the area under the graph, this is positive work done. Why this is positive work done? Because of expansion. The gas push up the piston. The gas do work done by gas. The gas do work. The gas do work. When expansion, volume increase, the gas do work done by gas, so work done is positive. So it refers to the second situation here. So when volume increase, when the gas do work, what happened to the internal energy? When the gas do work, it loses internal energy. Still remember? As I said, when work done by gas, the gas do work. He will lose energy. Why? It means that the gas is actually use up its own internal energy. To do the work. So he lose internal energy. The internal energy will decrease. So that when internal energy decrease, the temperature decrease. So that's why when going to the right, when expansion, when the gas, this volume increase means I should write the gas, when the gas do work. How it do work? When the gas do work, the gas does not receive energy from outside, no heat energy can enter. So the gas only has to use his own internal energy, use up his own internal energy to do work. When he uses up his own internal energy to do work, the internal energy will decrease. So that's why the graph will drop to a lower temperature line. It will drop to a lower temperature. Do you see that? It will drop to a lower temperature. You see? So when the gas do work, from V1 going to V2, the point cannot go, it cannot maintain at the same temperature. Because the gas has used up its own internal energy to do the work. So the internal energy of the gas has decreased. It has to drop to a lower temperature line. From T1, 400 Kelvin, drop to 300 Kelvin. Okay, so we can imagine like this. When the gas push the piston up, he actually is using his own internal energy to do the work. When he uses up his own internal energy to do the work, his internal energy will surely decrease. So internal energy decrease means the graph cannot maintain on the same isothermal line, but it has to drop to a lower isotherm line, or it has to drop to a lower temperature. So because it has to drop to a lower temperature, that's why the graph of adiabatic process is steeper compared to isothermal process. Isothermal process, it doesn't use up, when he do the work, he doesn't use his own internal energy to do the work. He uses the heat energy that enters, because for isothermal process, it is a good conductor container. The heat can easily go in. So the gas, it does not use its own internal energy to do the work, but the gas actually uses the heat energy that enters to do the work. So the gas doesn't lose any internal energy. So that's why the graph can maintain on the same isothermal line, maintain on the same temperature, because he doesn't use up his own internal energy to do the work. He uses up the energy from outside. He uses up the energy from outside, the heat energy, to do the work. He doesn't use up his own internal energy to do the work. He uses up the energy that enters from outside to do the work. So he doesn't lose any energy. So it maintains its internal energy, it maintains its temperature. It maintains on the same isotherm line. Why he can easily use the heat energy that enters? Because it has good conductor container. But for adiabatic process, no help from outside. Because it's well insulated. The heat cannot enter. No help from outside. So what the gas have to do when expansion? So the gas has to use his own internal energy to do the work, to push the piston up. He has to use his own internal energy. He uses up his own internal energy to push the piston up. He use up his own internal energy to do the work. So his internal energy surely drop. It cannot maintain on the same isotherm line as the isothermal process. So when he do the expansion, when the gas do the work, he use up his own internal energy to do the work. It cannot maintain on the same isotherm line 400 Kelvin. But when he use up his own internal energy, his internal energy decreased to a lower internal energy, and it dropped to a lower temperature. It dropped to a lower isotherm line. So when he use up his own internal energy to do the work, he cannot maintain at the same isotherm line because his internal energy has dropped. His internal energy has dropped. His temperature also dropped to a lower isotherm line. So that's why adiabatic curve is steeper compared to isothermal line, because adiabatic process use up his own internal energy to do the work. His internal energy will decrease and his temperature will decrease to a lower isotherm line. Okay, that's the meaning and comparison between isothermal process and adiabatic process. Now, the last one, the work done. For adiabatic process, it certainly has work done because it has area under the graph. You see that? It has area under the graph. But in metric syllabus, it is out of syllabus. Yeah, we don't study how to calculate. We don't study how to calculate the work done for adiabatic process. It is out of the matriculation syllabus. Okay, so in matriculation syllabus, we don't study how to calculate the work done for adiabatic process. There is work done, but we don't study how to calculate the work done. But there is work done. Okay. I did say that there's work done by the gas. Yeah, he uses up his own internal energy to do the work, but we don't calculate the amount of work done that is done. Yeah, for adiabatic process, we don't study the equations how to calculate the work done for adiabatic process in metrics. Okay, so that's it for adiabatic process, and that's all for our chapters. I hope you understand all the series of the summaries. Hope you stay tuned. We still have the videos for problem solving in this chapter coming up. Okay, stay tuned for that. And thank you for your time. Bye.